An advanced AI model like GPT-4 requires the same amount of electricity as a small town, drawing power from thousands of liquid-cooled servers humming in a multi-million-dollar data center. Yet, right now, a model with nearly identical capabilities is running offline, inside a 5-watt smartphone in your pocket. This is not a software trick. It is a mathematical paradox. For years, the industry assumed that intelligence was directly tied to scale, that you needed warehouses of silicon to generate coherent human language. But a quiet breakthrough has flipped this assumption on its head. By rewriting how computers represent information, engineers have managed to shrink giant models to a fraction of their original size without destroying their intelligence. The secret is not better batteries or faster chips. It is a process called quantization, and it is quietly changing how we interact with machines. To understand how we got here, we have to look at the physical reality of how an AI model thinks. A modern language model is essentially a massive collection of numbers called weights. These weights act like dial settings on a vast control panel, determining how signals flow through the network. In standard models, each of these weights is stored as a 16-bit floating point number. This format allows for incredible precision, capturing tiny variations in numerical values. But precision comes with a massive physical cost. A 70 billion parameter model saved in this 16-bit format requires over 140 gigabytes of random access memory just to load. Your smartphone, at best, has 8 or 12 gigabytes. This is the 16-bit weight wall. It is a hard physical ceiling. If you try to run a raw, uncompressed model on consumer hardware, the device simply runs out of memory and crashes before the model can even say hello. Imagine you are an artist trying to recreate a hyper-realistic sunset. To capture every subtle shade of orange and purple, you use a massive palette containing 65,000 different custom-mixed oil paints. This is 16-bit precision. It is beautiful, but storing and transport testing thousands of heavy paint tubes is incredibly difficult. Now, imagine someone hands you a box of only 16 crayons and tells you to paint the exact same sunset. This is the essence of 4-bit quantization. You are forcing a system built on infinite gradients into a tiny, coarse grid. If you simply round every number to the nearest crayon color, you lose the subtle details. The orange sky turns into harsh, flat blocks of color. In an AI model, this raw rounding is called quantization error. If you do it poorly, the model loses its ability to comprehend context, generating gibberish because its delicate mathematical relationships have been shattered. For a long time, researchers thought low-bit quantization was a dead end because simple rounding destroyed model performance. But in 2023, a landmark paper introduced a breakthrough called QLoRA, which introduced a mathematical concept known as normal float 4. The creators of this technique realized something profound. The weights in a trained neural network are not distributed evenly. They almost always form a classic bell curve, clustering densely around zero. Standard computer formats divide numerical space into equal, uniform steps, which waste valuable memory on extreme values that rarely occur. Normal float 4 solves this by creating a nonlinear grid. It places most of its 16 available 4-bit markers right in the middle of the bell curve where the weights actually live. By aligning the mathematical grid with the natural distribution of the model's brain, we can compress 16-bit weights down to just 4 bits without losing the critical nuances of the model's intelligence. But compressing giant models is only half the battle. The industry is currently moving along a dual track. While we are busy squeezing existing giants down to pocket size, researchers are also taking a completely different approach, building tiny language models from scratch. Instead of training a massive multi-billion parameter model and then shrinking it, engineers are now designing models that are structurally optimized for edge devices from day one. These tiny models are trained on highly curated, high-quality synthetic data, allowing them to punch far above their weight class. They do not try to know everything about world history or write complex software code. Instead, they are hyper-specialized for local tasks like on-device search, email summarization, and natural language interfaces, proving that a lean, well-trained model can often outperform a compressed giant. Software math is useless without physical hardware to run it. If you tried to run a quantized model on a traditional mobile processor, it would still drain your battery in minutes because CPUs are not built for this specific type of math. This is where modern mobile silicon comes in. Today's smartphone chips feature dedicated neural processing units, or NPUs. These are specialized hardware accelerators designed to perform low-bit integer math at blistering speeds with almost zero power consumption. When paired with open-source runtimes like llama.cpp and file formats like gguf, the hardware can bypass the main processor entirely. Instead of converting the compressed 4-bit weights back into heavy floating-point numbers to read them, the NPU can run the calculations directly on the compressed integers. This hardware-software synergy is what keeps your phone cool to the touch while it generates text locally. But this incredible efficiency comes with a silent, heavy trade-off. When you compress a model's weights, you are forcing it to operate with fewer intellectual shades of gray. This compression does not affect all tasks equally. While a 4-bit quantized model might still perform exceptionally well on standardized tests or factual recall, it struggles with edge cases, cultural nuance, and complex reasoning. More concerning is the phenomenon of bias amplification. Because quantization cuts away the low-probability nuances of a network, the model naturally falls back on its strongest, most dominant statistical associations. This means that quiet, systemic biases embedded in the training data can become loud and rigid in a compressed model. If a teacher uses an offline, quantized AI tool to grade student essays in a rural area without internet, that local model may penalize non-standard dialects far more harshly than a full-sized cloud model would, running its silent, biased evaluations entirely offline without any central audit trail. We are entering an era of quiet, decentralized intelligence. The transition of AI from giant cloud data centers to local, quantized execution on your personal devices is more than just a technical triumph. It is a fundamental shift in digital sovereignty. When your models run locally, your private conversations, personal schedules, and sensitive documents never have to leave your physical device. You are no longer renting intelligence from a distant server for a monthly fee. You own it. But as we embrace this private, offline future, we must also accept its responsibilities. We are trading the transparent, easily audited servers of the cloud for billions of tiny, unmonitored black boxes running in people's pockets. The math of quantization has successfully squeezed a giant into our phones, but it is up to us to decide what kind of thoughts we want that giant to think.